Okay, our session's being recorded. So here's another example where we're going to need to use integration by parts. Let me give you a moment to copy that example down. Okay. Let me just see here one moment here. I see a little question from Esther, I believe. I don't know why I can't see it here. Hold on. Esther, I'm sorry. I saw you chat, ask a question, but I can't see it for some reason in my thing here. But
I can tell. I can speak.
oh, okay.
So I have a question about the problem on section 5.6 on WebAssign. And I don't know if should I visit you on office hours or
Yes.
you can do after class?
Yeah, I have office hours right after class. And you know, you just like in Blackboard, like how you got in the class session here, there's another session for the office hour. Yes, please see me after class and we can discuss your question.
Okay, yeah, thank you.
You're welcome. All right, so here we have the integral from 1 to the square root of 3 of the arctangent of 1 over x dx. And we need to find the antiderivative of this. So, of course, we remember our integration by parts. Integration by parts says that the integral of u, I try to write it the best I can, u dv equals u times v minus integral of v du. And this is one of the harder integration by parts problems. But as you know, you have to decide what u is going to be, and you have to decide what dv is going to be. And how many of you over the weekend did you did an integration by parts problem where you assigned u to something and dv to something, and it didn't work, and the problem got worse? How many had a problem like that where maybe, it got worse? Okay, Sene knows what I'm talking about. Michael, Adriana. Okay, many of you. Tariq, Esther, Alan. Yeah, sure. So of course, then what you have to do is you have to change what you're letting u equal to, and you have to change what you're letting dv equal to. So it's sort of like sometimes you just have to try something and see if it's going to work. And for this problem here, what we're going to do is we're going to let u equal the arctangent of 1 over x, and du will equal dx. We're going to try that because it worked for, you had a problem where you had the integral of the arctangent of maybe like 3t dt, something like that, and it worked letting u be the arctan. So let's go to the solution. Okay, so in our solution, we're going to let u equal the arctangent of 1 over x. 1 over x is x to the negative first, and dv will equal dx. Okay, so we have our integral u dv. Okay. Okay, and as you know, what we have to find is what v is, and what du is. Right? Once we know those, we can apply the integration by parts formula. Okay, so let me give you a moment to copy that. All right, now let's see here if there's anything. So when u equals the arctangent of x to the negative first, then we have to get the derivative of u with respect to x, right? So for this, we're applying the chain rule, right? We're applying the chain rule here. The derivative of the arctangent of a number is 1 over 1 plus the number squared. Well, I should say the derivative of the arctangent of a function. I want to say this the right way. The derivative of the arctangent of x is 1 over 1 plus x squared. Well, we have an x to the negative first as our function here. So the derivative with respect to x of the arctangent of x to the negative first is 1 over 1 plus x to the negative first squared times the derivative of x to the negative first, which is negative x to the negative second. Now this on the right looks like something, you know, this here, our expression on the right here looks like something we definitely should try to simplify. So I write x to the negative first as 1 over x, and x to the negative second is 1 over x squared. Okay, and actually I do need a dx here, don't I? I do need a dx here. Okay, and so if you know, we're at this stage here now, and if you multiply the numerator and denominator by x squared, that's just like multiplying through by 1, right? So then the final expression for du will equal -1 over x squared plus 1 dx. Okay, are there any questions on the getting that expression for du? All right. And dv was dx, so v equals x. And so now when you apply the integration by parts, your integral I, remember we always call the integral I, and you saw that has advantages to do that. If I apply integration by parts, my integral I is going to equal x times the arctangent of x to the -1st, evaluated at 1 and √3. Okay, because those were our limits. Minus the integral from 1 to √3 of x times -1 over x squared plus 1 dx. And the limits don't change. This is when you do a substitution with a definite integral, the limits change, but not with integration by parts. The limits do not change because you're not doing a substitution. Okay, let me know, are there any questions on up to this step here?
I have a question.
Oh yes, Kyrie.
Why did you decide to multiply the numerator and denominator by x squared?
Okay, good question. So on this step here, I multiplied by x squared just because on the top and the bottom, numerator and denominator, just because I wanted to simplify du. This expression here, I'll circle it in green. This expression looks complicated to me. Looks complicated. It's a complex fraction. You have a fraction divided by another fraction. So I just wanted to rewrite the fraction in a nicer way. You don't have to do that, but you'll be glad you did. Okay, are you comfortable with that, Tyree?
Yeah, thank you.
Okay, very good, very good. Are there any other good questions? All right, I'll go ahead, move to the next page if everybody has this copied okay. Okay. Well, so now my integral, this first step is basically, I just recopied what I had on the previous page. And naturally, I'm going to put in the square root of 3 for x here, and the 1 for x there, where those arctangents are. And I still have to evaluate the integral of x over x squared plus 1. But what can I use? What technique can I use to do that? Yeah, Felicity, question?
Isn't there a minus between?
Oh, all right. Hold on. We'll come back. Hold on. The thing is, you did have a minus here. You're right, but you have a minus here, and so minus is a plus.
I see. Thank you.
Okay. Good question. Good question. All right. So okay. To evaluate this last integral here, what approach are we going to use? Integration by parts or substitution?
I have a question.
Oh, yes, Candace.
For the integral x over x squared plus 1, I understand why you brought the negative out, but it was a 1 over x squared plus 1 on the previous page, and now it's an x over x squared plus 1. Is there a reason for that?
Oh, let me see. Hold on one moment. Maybe I have a typo. Let me check here. Oh, here's the x. And then here's the...
You just multiplied it. Okay, thank you.
That's right. That's right. All right. Very good. Very good. All right. Good questions. Okay. So how are we going to handle this last integral here? What do we have to do to integrate that? You've learned two techniques, integration by parts and substitution. Rodrigo thinks substitution is the way to go, and I agree. I agree, it is. Okay, so let's see. Let's move down a little bit here in the work. Of course, we're going to let, in that integral, we'll let u equal x squared plus 1. So the next dx will equal 1/2 du. And in regards to computing these arctangents, you have the arctangent of 1 over 3, and you have the arctangent of 1. Okay, I drew 30, 60, 90, and 45, 45, 90 triangles for you. Okay. Now you can always bring up on the internet they have charts of the unit circle with all the special angles and the special values. You know, but I like to, I just put down the two, well, the two of the key triangles. Okay, so what would the arctangent of 1 over, the arctangent of 1 over root 3? So, you know, when you take the tangent of an angle and you get a number, you then, you know, the reverse is taking the arctangent of a number and getting an angle. Of course, the angle is in radians. But tangent is defined as you know, opposite over adjacent. So the tangent of what angle, I'm looking here now in this 30, 60, 90 degree triangle, the tangent of what angle is going to equal 1 over root 3?
30 degrees.
30 degrees. So therefore, the arctangent of 1 over 3 is going to equal, if the tangent of 30 degrees is 1 over root 3, then the arctangent of 1 over root 3 equals what angle? That's right, Kahindi, 30 degrees. Or pi over 6. Okay. So whenever I encounter these arctangent problems, I like to sketch a little one of my special right triangles. Just kind of helps me feel comfortable. Now the arctangent of 1 over 1, which is the arctangent of 1, the tangent of what angle is going to equal 1? The tangent of what angle equals 1? That's right, Rodrigo, pi over 4, or 45 degrees. So if the tangent of 45 degrees is 1, then the arctangent of 1 equals 45 degrees, or pi over 4. Okay, so I'm just showing you how we got these values here. And you always, when you do the arctangents, you're computing integrals, the angles have to be in radian mode. Okay, are there any questions down to this step here? All right, well, of course, we did a substitution. We let u, on this integral on the right, we let u equals x squared plus 1. Well, that means, of course, our x limits of root 3 and 1 get transformed. So now we have an integral with respect to u, but the limits of root 3, well, the x limit of root 3 becomes 4, because 4 is just root 3 squared plus 1. And the x limit of 1 becomes 2, because, you know, u is x squared plus 1, so 1 squared plus 1 is 2. And now it's just very standard how to complete this problem. The antiderivative of 1 over u, you know, we factor the 1/2 out in front of the integral there, and the antiderivative of 1 over u is the log of the absolute value of u. Let me give you a moment to catch up on that. Are there any questions leading up to this step here? All right, well, then let's just, you know, finish the problem here. So the log of, for the antiderivative, which was the log of the absolute value of u, we put in the 4, we put in the 2, and the difference of the logs is the log of a quotient. The difference of the logs is the difference of the quotient. So, okay, Tina, good question, good question. Tina's wondering why she wants justification on this step here. Why the log of 4 minus the log of 2 is the log of 4 over 2. Well, if you have the log of A over B, okay, A and B are positive, of course. Do you recall that that equals the log of A minus the log of B? How many recall that as one of their log rules? That's right. Thank you, Felicity. Yeah, so the log of a quotient is equal to the log of the numerator minus the log of the denominator. How many does that ring a bell for you? I hope we have more than one person who, okay. Thank you, Tina, Eric, Michael, Felicity. All right, so I mean, WebAssign, let's see, Sir Raphael says, wouldn't the 4 be B and 2 be A? Well, no. So Sir Raphael, what I'm doing is, you agree that the log of A over B equals the log of A minus the log of B. Well, I have the log of 4 minus the log of 2. So A is 4 and B is 2. Okay. So, well, the log of 4 2/2 is just, well, Tina, WebAssign would accept this answer here. This answer here, WebAssign would accept. But, you know, I just wanted to make the answer look a little more succinct, a little more attractive. When I have the difference of 2 logs, I like to write it as the log of a quotient. Okay, so both answers are right. Both of these, you know, WebAssign would take either answer. All right, are there any other good questions? All right, I'll move on to the next example, but as everybody have this copied down okay? All right, very good, very good. Well, let's move to the next example. Okay, now this is an example that comes up in differential equations, this integral. Let me give you a moment to copy it down. Okay, so let's see here, one moment. All right, so we have the integral from 1 to 4 of e to the square root of x power dx. What makes this integral difficult? Felicity?
The power is not just a number.
That's right. Well, yeah, it's the square root of x. That's right. If it were something like this, if it were the integral of e to the u du, you know, with some numbers here, you know, just some numbers there, would we be happier? Are we happier with the integral of e to the u du? Is that something we can get the antiderivative for? That's right. We can. Thank you. Thank you. Candy, Tina, Tyreek, and Justice. So we're going to make a substitution first. Before we do anything, we're going to make a substitution. Not Nell, do you have a question? You're good? Oh, okay, okay. So we're going to do a substitution, and what we're going to do is we're going to let u equal the square root of x. That's the same, of course, as saying let u equal x to the 1/2 power. Because we know we're not going to be able to get, we know that we got to simplify this integral. So let's go to the next page. Okay, here we're making the substitution. U equals the square root of x, which equals x to the 1/2 power. And then I take the derivative of u with respect to x. Using the power rule, we get du dx equals 1/2 times x to the negative 1/2 power. Okay, so just on this integral, we're replacing e to the square root of x with e to the u. And now we have to figure out what dx is going to be. What is dx going to equal? And obviously the two limits will get changed. The 2x limits will become u limits of the x limit of 4 will become 2 because the square root of 4 is 2, and the x limit of 1 will become the u limit of 1 because the square root of 1 is 1. So it's easy, except we got to find dx. So okay, well, if du dx is 1/2 times x to the negative 1/2 power, then du is 1/2 times x to the negative 1/2 power dx. Now we have to get dx alone. We have to get dx alone. Okay. So, of course, we can multiply by 2 both sides. 2 times 1/2 would be 1, but we still have that x to the negative 1/2 power there on the right side. So what I'll do is I'll multiply both sides of this equation by x to the 1/2 power. Okay, so what I'm doing is I'm taking x to the 1/2 power and multiplying that on the right side here, and I'm taking x to the 1/2 power and multiplying it on the left side of the equation. Now, why do I do x to the 1/2 power? Well, on the right side we have x to the 1/2. On the right side here, we have x to the 1/2. We have x to the negative 1/2 now times x to the 1/2. But when the base is the same, what do you do with the exponents? We have a base x. We're taking x to the negative 1/2 times x to the 1/2. What do we do with the exponents? We add them. That's right. Thank you. Thank you. And so we get x to the 0. But what is x to the 0th power equal to? 1. That's right. Thank you. Thank you. So therefore, on the right side, I have 1/2 times 1 dx, because x to the 0th power is equal to 1. So it's like 1/2 times 1 dx. And then I got, x to the 1/2, the u on the left, but x to the 1/2 was equal to u. we let u equal x to the half in the substitution. And so therefore, it turns out that dx is going to be equal to 2u du. Oh, right. What I'm doing here, of course, is I'm multiplying both sides by 2 for that equation there. And so dx becomes 2u du, and now we have our new integral. Our integral I is equal to the integral from 1 to 2, because those are our new u limits. The integral I equals the integral from 1 to 2 of e to the uth power 2u du. Okay, are there any questions on that? Tina's good. All right, wonderful. Notnell's good. Excellent. Esther's all good. All right, excellent. Well, you know, was this a good decision? Eric likes it. But now we have this integral. You know, and this integral, of course, I can write it as 2 times the integral of 1 to 2 of u times e to the u du. This integral here reminds me of, I mean, have you seen this kind of integral before? Maybe in your homework. I mean, the 2's there, of course, but does that look familiar? That kind of integral? I mean, if you had the integral, let's say you had, just as an aside, let's say instead of integral of u times e to the u du, let's say you had the integral of x times e to the x dx. How would you integrate that? Would you use, okay, Rodrigo says by parts, Tina says by parts, Michael says by parts. Okay, so we have this integral here now that we have 2 times, you know, the integral from 1 to 2 u times e to the u du. Well, the variable's different, but the concept's the same. We can use integration by parts to integrate that, and so that's what we're going to do. All right, I'll move to the next page then, if we're good. Okay. Well, all right. So let's use integration by parts. So in this problem, what we're doing is we did a substitution first and then integration by parts. But we have to be a little bit careful, because what you're used to is the integration by parts formula is integral of u dv equals uv minus integral of v du. This is what you're used to. You know, how many have that formula kind of memorized in their brain? You know, maybe burned into their brain. The integration by parts formula. Okay, getting there. All right, Tina's getting there. Well, the thing is, I've already used my u variable to make a substitution in this problem. So it's confusing if I were to say let u equal u and dv equals e to the u du. It's a little bit confusing. I want to have a little independence. I don't want to reuse a variable that I already used. So based off this first integration by parts formula, I'm going to make another integration by parts formula, where I have the u is the variable that I've used. So instead of u, why don't I have w in place of u? Then the integral of w dv would be wv minus integral of v dw. I mean, there's nothing wrong I mean, that integration by parts formula, that second one is correct also. Okay, are we comfortable with that? I'm just replacing the U with the W. Okay, good, good. So, okay, well now I'm going to use the second integration by parts formula here. And we're going to let W equal U. W is going to equal U. And EU du will be dV. And so now we just go through the steps on the integration by parts. And so the integral will equal what we have here. Okay, give you a moment to catch up here. Are there any questions? All right, Rodrigo's comfortable. So of course now the U limits stay 1 and 2. They stay as 1 and 2 because we did an integration by parts. And the limits don't change when you do integration by parts. So, okay, well, then we just proceed on to solve the problem. Now we have for our integral, we have well, what I mean is the U times e to the U, we evaluate that at 1 and 2. And we have the integral of EU du. We're happy with that. The antiderivative of e to the U is e to the U. And so now it's just basically computation. And in the end, you're going to wind up with your answer as 2 times e to the squared. That's going to be the integral. That's the area underneath the curve. That's the area underneath the curve e to the square root of x when x goes between the values of 1 and 4. That's the area bounded above by the function e to the square root of x power, and below by the x-axis between the values of x equals 1 and x equals 4. Okay, I'll give you a moment to copy that. All right, are there any questions then? All right, I'll stop the recording.